Yeah, so today's talk will be about, as Alba said, normalizing flows and diffusion models. And we'll talk about both how they are used for images and for text. So this is based on a recent paper that will be presented at NeurIPS 2021 now in December, which actually work on these two model classes, and we focus on text. But since this is a computer vision seminar, I thought I should also talk about images. And also, luckily, most work in these model classes have been done for images. And also, I assume that most people aren't really familiar with these model classes. So I will actually talk more, I will give more like an introduction to these types of models and kind of talk a bit about how they're used for images. And then I'll just briefly mention what we have done so that they can also be applied to text. So here is the paper that it's loosely based on. It's on argmax flows and multinomial diffusion. So I'm not going to read the full abstract, but just the first two sentences. Flows and diffusion models have mainly been trained on ordinal data, such as natural images. But in this paper, we introduced two extensions, one of flows and one of diffusion models, such that they can also be applied to categorical data, such as, for example, text. So yeah, this is joint work with these amazing people, all at least at some point based at the University of Amsterdam, although some people have moved from there by now. Yeah, so both flows and diffusion models are generative models. So why do we need generative models? It's a good question. So the main operation we can do with a generative model is generate data. So that is sample from our distribution. And there are many applications of this. Some are that I could think of are image segmentation. So all of these are really conditional sampling. So there's also like a conditioning here. But any unconditional generative model can also be made conditional. So yeah, image segmentation where you condition on some image and you want to output a segmentation map. Machine translation, you condition on a French sentence and you generate a German sentence. Speech to text, where you speak to Siri on your phone and it converts that to text, and vice versa, text back to speech. And for example, drug discovery, where you want to generate molecules that have certain properties, for example, could be another example. Additionally, some generative models allow you to compute the density of data. So when you have an image, you can put that into the model and ask for the log likelihood of that. And this is useful, for example, for compression. So you can do lossless compression with this, and potentially also for anomaly detection. Although there's some work saying that it maybe doesn't work so well for this, so it's kind of an open question. Yeah, so we would like to do maximum likelihood training with this. So we have a model P with some parameters theta, and we train that either on images, so a set of images like this, or on text. So here I used essentially DNA sequences, but you can basically treat them as text and model them like this. And we would like to do so using maximum likelihood estimation, which is probably familiar to most of you. So the question is, how can we build expressive distributions that can model this very complicated objects, images, text, etc., that also allow us to do this maximum likelihood training? And so there are a few different model classes with different benefits and drawbacks. So the first one, GANs, they are known for generating great samples. They're fast to train and sample from, but the likelihood is not defined. And possibly as a result of this, training can be quite unstable. They're kind of hard to work with. Then we have energy-based models. The great benefit is they're not really constrained in any way, and that's also the drawback, because it means everything is intractable, including computing the likelihood and sampling from the model. Then we have VAEs, which is this latent variable models that also allow fast training and sampling. But because of the latent variables, the computing the likelihood is intractable. Autoregressive models, they have exact likelihoods, and they tend to perform very well on likelihoods, so they tend to have state-of-the-art likelihoods. The drawback of regressive models is they are very slow to sample from. So you have to sample sequentially, one dimension at a time. So for an image, that would require you to sample one pixel at a time. And for each time, you have to evaluate a full neural network. Then we have the first class that we'll actually talk about today, which is flows. So the great benefit of flows is they have exact likelihoods, and they also have fast sampling. But the drawbacks is you have to, to get this to work. So if you want this exact likelihood and the fast sampling, you have to construct very constrained architectures. So that can be a limitation of those. And lastly, the second model we will talk about, diffusion models. They have kind of started becoming popular in the last year or so. And are really, they've now gotten state-of-the-art in likelihoods and sampling quality, so they apparently work really well. The drawback is that computing the likelihood is intractable, as it is in VAEs, and sampling tends to be also quite slow, although you can, there are ways of speeding this up a bit. So, to the outline. First, we'll talk about flows for images. And then we'll talk about flows for text, and then we'll do the same for diffusion models. First for images, then for text. So most work, as I've said earlier, has focused on images. So that will be this part. And then our work focused on doing this for text. And there's some other work that has on flows that have also worked on text. I won't really go through that here due to limited time, but I'll talk a bit about our work just very briefly. And diffusion models for text, I think we were the first to do that, so I will also mention that a bit. So I will come back to this outline in between each of the part and kind of fill in a little summary here. So first we'll talk about flows for images. So a little bit of history first. Normalizing flows, the term originates from these papers, and it describes a change in probability density as you pass samples through a series of invertible maps. This term was later popularized by Resenda and Mohammed, so this is what really pushed it into the machine learning community, where they used normalizing flows for building flexible posterior approximations, so variational inference for Bayesian posteriors in variational autoencoders. Separately, the first generative flows for generative modeling, and that was really scalable, was first NICE that generated these CFAR images, not very good, but it was a start. Then Real MEP, which was a follow-up to this paper that improved performance a lot. I should say in these papers, actually, the term normalizing flows was not used, but this has become the kind of the main term that people use for these types of models now. So you could say these were the first really scalable generative flows. So flows, how do they work? So to construct some distribution P of X, so where X could be our image or images, we use two things. We use a base distribution, P of sets, and a mapping F. This is some deterministic mapping, could be some form of neural network. And the base distribution, P of sets, that's the one up here, is typically something simple like a factorized Gaussian, so Gaussian 0, 1. And we take samples from that, and we map it through this deterministic mapping to get samples in the X space. And this kind of warps this density into some potentially much more complicated density down here. And so this might sound a bit like a GAN, for those who are familiar with those, and it is very similar to that. The difference is, for normalizing flows, we require this F to be a bijective or invertible mapping. So this means the space set and X have to be of the same dimensionality. And we have to construct some F that is invertible. So we're a bit constrained in that sense. But as a benefit of this, we can actually compute the log likelihood. So we can use the change of variables formula, which includes this Jacobian determinant term and the log base density here. And so yeah, this Jacobian is just the partial, like the Jacobian of this transformation. So the partial derivative of all the variables in set with respect to all the ones in X. And yeah, we have to compute the determinant of that. So we'll get back to this later, how we can do this efficiently. So the benefit of this, or one benefit, is that bijections are composable. So we can construct a more flexible transformation by stacking multiple layers and getting kind of a deep flow, if you will. So we can use T layers like this. Sampling is, as you'd expect, you just pass them through all the transformations. To compute the inverse, you do the same. And the Jacobian determinant also decomposes like this, because essentially you have the chain rule for all these, the chain rule of calculus for all these derivatives in here. And then because the determinant of A times B is determinant of A times determinant of B and so on, it decomposes very nicely like this. So you can essentially just sum up the Jacobian determinants for each of these layers. So that's very nice. So essentially the name of the game for flows is how do we construct efficient layers like this that helps us construct very flexible flows. So yeah, we want to construct layers that are, number one, expressive, so they can perform some non-trivial transformation. Number two, they have to be invertible. This is a requirement. And number three, we want them to have cheap to compute Jacobian determinants. Because if we just do things naively, it will have a cubic cost. Computing the determinant is cubic in the size of the matrix. And the size of the matrix is the number of dimensions in the data. So you can divide flow layers, really, into a few different classes. So you have the ones that are based on determinant identities. In here you have planar flows, radial flows, celestive flows, etc. We won't really talk about those. We have autoregressive flows. They give you a lower triangular Jacobian. In here you find masked autoregressive flows, inverse autoregressive flows, etc. We won't really talk about those either. Then we have coupling flows, which you could, in some sense, say are a special case of autoregressive flows. They are also lower triangular, but they have an even more special structure that allow you to also sample quickly, which you don't really have in autoregressive flows. And then finally, there's this more recent flows, you could say, that either work in continuous time or use some approximations so that you can get unbiased estimates of your Jacobian determinant. And we won't talk about those either. What we will talk about is coupling flows, which you could say arguably is the most popular type of flow used in the literature. And also one of the kind of simpler to implement, and they're quite flexible and fast and so on. So coupling flows. This one. How do we get this structure for the Jacobian? So say we have some data X. So this could be our image. It has D pixels, and we want to transform that to some to like the latent space or to the transform variable set. What we do is we split the data into two parts. So usually roughly 50-50, but you can choose that. And then we transform the second half, this green one, and we do that conditioned on the first half. So we have some neural network that looks at the first half, and it outputs some parameters, mu and alpha, for example, that basically decides the transformation for the second half. So for an affine transformation, where we just shift and scale, could look something like this. So the first part is just identity so we identity transform this part. It's not really touched. And the second part, we scale with this alpha, exponential of that, so it's a positive number, and we shift with beam. The benefit of this is it's quick to invert. So we just have to essentially invert this this affine transformation here, very easy. We move mu over and divide by e2 alpha. And the first part is, of course, very trivial because it's identity. And that means when we're coming the other way during sampling, the neural net can just look at the identity transform part. So it's fast to go in both directions. And the Jacobian determinant is, I mean, because of the lower triangular structure of the Jacobian, it's really just the product of the diagonals. So in log form, it's the sum of the log diagonals, which is just the alphas for this d plus 1 to d. So can we just, I mean, coupling layers are quite expressive. They have a freeform neural network in them, so they can learn very complicated transformations. But are they enough? Can we just stack them? And I mean, from this image, you can clearly see that no, because here there is no mixing. So we will just transform the second half all the time, but the first half of the dimensions will never be transformed. So we need some form of permutation layers. So that could be, for example, a reversing of the transformation. So you basically just flip them around, or some kind of shuffling. And these are also just invertible transformations, volume preserving, trivial to invert, and so on. So these two things together, you can build very expressive densities. So for images, how do we do it? So it's essentially so this is taken from this paper, Kingma and Darival, 2018. So it's the GLOW paper, and they managed to generate get a model like this to work quite well. It was based on coupling layers that we discussed. So some additional things you do for images is you construct a multiscale architecture typically. So it means you factor out some variables earlier to kind of reduce dimensionality. So typically you kind of downsample the image to a lower resolution as you go up. The other thing is you split along the channels. So if you have these 3 channels here, then you condition on, say, the first 2, and you transform the third one. And this conditioning is typically done, as is usual with images. We use convolutional neural networks. Typically now also some form of self-attention is baked in there because it can further improve performance, but it's typically based on some form of convolutional network. And you can, instead of reverse or shuffling, you can do one-by-one convolutions, which can kind of be seen as a learnable permutation, which they showed in the GLOW paper. This improves performance. So I mean, with all these things combined, you essentially get what they used in the GLOW paper, and you can model high-dimensional images very well. So that is a very short introduction to flows for images. There's, of course, a lot more detail to this, but I have to move quickly due to limited time. So a quick summary of this is we use some invertible transformation like this, and we can learn a distribution over images that we can generate from, and we can also evaluate the density for new images. So now we move on to the part on text for flows. So a detail I've swept under the rug so far is that images are actually ordinal. So that means they're discrete and they have ordered categories. So these are kind of like the pixel intensities, typically from 1 to 255. And for 1 pixel, it might look something like this. So you have discrete data down here, and this is your flow up here, some continuous model. Now the problem is if you try to train this flow directly on the data, and you kind of you ignore that it's actually discrete. You just treat the integers as continuous variables. The flow will, or the flexible continuous density, the flow will learn to essentially hack that. So that it will hack the fact that you have a finite support. So what you can do is place like, imagine like a mixture of Gaussian. So if you place one component on each integer, and then you take the variance of each of those components to 0, you will get infinitely high log likelihood. And you can do that even without modeling any structure in the data whatsoever. So there is a mismatch if you try to directly train a continuous model on discrete data. So this is what Uri et al. Noticed in 2013, and what they proposed is dequantization. So it works essentially like this. You take your discrete data. So if you observe a 5, you add uniform noise so that it ends up between 5 and 6. And then you train your flow on that. So this is now a continuous density that fills the whole space, and the flow doesn't collapse on kind of the integer support. Yeah, and this was later showed to provide a lower bound on the actual discrete log likelihood that you would get if you actually integrate this flow into the different bits. So actually, we do need some trick like this when we're training flows on images. So could we just also apply this to text? And I mean, the answer is yes, we could, but the categories are not ordinal. So this could be like different words, for example, in a text setting, and there's no notion of one word being closer to another beforehand. This is usually some very arbitrary ordering. And so it's less natural to use dequantization like this. And we also show this in the paper that this actually performs worse if you try to naively do this. So yeah, before we introduce argmax flows, I want to just quickly show talk about how another way of looking at this that kind of provides the setup for argmax flows. So in this paper from NeurIPS last year, we introduced surjective flow layers. So that's layers that are not invertible. It's a deterministic map, but two inputs can map to the same output. And that's clearly not invertible, but we use the fact that all surjective layers have something called a right inverse. So that is a function that maps from x to z, such that when you map back, you get back to the same x. So that for this one, it could be any one of these two. And this is not unique, the right inverse. So what we do is use a distribution over all these right inverses, and we call that a stochastic right inverse. So dequantization that we just talked about can actually be viewed as a surjective layer like this, where the deterministic transformation is a flooring operation. So any number between 5 and 6 will become a 5. And then the stochastic right inverse for that is, for example, this uniform distribution that will map your 5 back to anywhere between 5 and 6. And this is really the setup that we used for argmax flows. So what we do is we introduce another deterministic transformation that is not invertible, the argmax operation. So that is, if you want to model 10-dimensional categorical data, you use 10 continuous dimensions, and so you kind of generate a continuous vector of size 10, and then you argmax that to get your discrete category. So to kind of invert this, or stochastically invert this, we again use this stochastic right inverse. So any distribution like this that has support over sets that would map back to x. So that is essentially any vector where, like if x is 3, it's any vector set where element number 3 is the largest, because that would map back to the same x. And yeah, that's really long story short on how this works. So we compose a flow here, this G. This is typically some coupling flow that we talked about earlier. and we get some continuous density, and then we argmax that to get the text. So when we train, we put text in and we pass it through the stochastic right inverse, and we train essentially the flow on that. I should say the likelihood and everything is kind of well defined here. I'm not going into the details. So here are some samples that we generated from this using either an autoregressive flow or a coupling flow that we talked about before. And you can see it learns to generate kind of reasonable text. And for coupling flows, it's a bit worse, but I think this is due to us using not really as many. We used like 8 layers, I think, so which it would probably work better if you go deeper than that. So back to the outline. So first, there's one thing we didn't mention in flows for images before, and that's this dequantization part. So for text, everything works very similarly. We use invertible transformations like this to transport a continuous density. And then instead of dequantization, we use this argmax layer instead. So this is kind of a rounding operation. This is an argmax operation, and then we have a stochastic inverse for those. And this way we can train flows on text data and generate reasonable text also. So that's the part on flows. And then now we'll talk about diffusion. This part is a bit shorter. Yeah. So diffusion models. Quick overview of those first. First introduced by Soldigstein in 2015. And it went relatively unnoticed, I would say, until last year, where Jonathan Ho and collaborators introduced this, denoising diffusion probabilistic models, or DDPMs. And what they showed is that, yeah, they essentially did some engineering tricks, you could say, on the original model, and some modifications of it, that makes it work much better. And that provided really great sample quality. And they also, with these modifications, provided a connection to score-based models, which is another type of models related to energy-based models that people have been really excited about. And then since then, there's been lots of progress. So in the last year or so, and this year, OpenAI had this paper, which showed that they actually now can beat GANs on image synthesis. So this is really interesting because GANs have really been known to be like the go-to model for if you want to generate nice images, it's the go-to model, and it's been like that for a long time. So now they have state-of-the-art samples there. Additionally, this paper from Google showed that they also actually have state-of-the-art log likelihood. And this is also interesting because this kind of benchmark has been dominated by autoregressive models for several years. So, I mean, before it was like, if you want to generate nice images, it's GANs. If you want good likelihoods, it's autoregressive models. But now it seems you can, with these diffusion models, you can kind of get both in one model. So that's really exciting. So the question is, how do they work? So down here you have some your data distribution. So here you really have some samples, some images, and then you transport that. You want to transport it to some Gaussian up here, and the way you do it is using T steps. So T is typically something like 1,000 or a few thousand, and at each step you do a very simple transformation. You add a little bit of Gaussian noise. So it's really just a noising process. And there are no learnable parameters in this part. I should say, for those that know variational autoencoders, it's actually set up exactly like a variational autoencoder, but where Q has no parameters and have this very simple kind of encoder, if you will. So yeah, it just adds noise gradually until your data has become a Gaussian. So for images, it looks like it. You can see less and less. It's more and more random until it's just completely scrambled up here. And then we learn distribution P that learns to essentially undo this noising process or denoise the data. And this is learnable. So here we use some Gaussian like this, but it's parameterized by a neural network that takes in the kind of slightly, or the noisy version of the image and outputs a slightly less noisy version of that image. And the nice thing with these types of models is that you can decompose the elbow, so the evidence lower bound, for those that know variational inference. So this is the training objective. You can decompose that into these T+1 parts, where the kind of the first one and the last one are special, but all the ones in the middle are these KL divergences. And actually, all of these are relatively easy to compute. So we can use we can train them very efficiently by sampling these terms of the objective. And we use that. In fact, this is a Gaussian, so you can jump from your data to any noisy version of that data in one go. So like 500 steps, you just do essentially this 500 times. This is, you can of course compute in closed form. So that goes here. Then using base rule, you can also compute this guy in closed form, which is kind of Q going the other way, but conditioned on the data. Also using, it's all Gaussians, and with base rule, you can compute that. And then the last guy is this, which is our decoder model, which is also a Gaussian. So everything here is really diagonal Gaussians. So this KL divergence, we know how to compute it. It's very simple. And I should say also that this is top one. It's just factorized Gaussian 0, 1. So it's also very simple. So yeah, that's essentially why you can use 1,000 layers or several thousand layers without running out of GPU memory. Is that you can at training time, you can essentially kind of, I like to think of it as Monte Carlo sample the layers you want to train. And this makes them very efficient to train, and is potentially part of the reason why they work really well. So that is diffusion models for images. So the process is like this. We don't use an invertible transformation, but we use a stochastic transformation that kind of gradually adds noise. And then we learn a kind of a decoder or a generative part that learns to denoise the data very slowly over something like 1,000 steps. And this distribution is some simple Gaussian. So we just add a little bit of Gaussian noise, and you can generate really, you can learn really complicated distributions with these types of models clearly, and learn to generate images quite well. So then it's for the final part, which is on how we did something similar to this, but for text. So our multinomial diffusion model. It's actually very, very similar. The setup is exactly the same, except our data is discrete, and the kind of the noising process is done using a categorical distribution. So at every step, instead of adding a little bit of Gaussian noise, what we do is, with some small probability, we randomly sample another category. So if it's like a string of text, at every layer, some of the characters will be randomly scrambled, and the rest will remain the same. And we do that over something like 1,000 layers until all your characters are essentially completely scrambled. So you can't really recognize the original text anymore. And then we use, very similar to before, we use learnable denoising process. So this P going the other way is a categorical distribution, again parameterized by a neural network. And just as before, the elbow decomposes like this, where, yeah, this P, this is the same as before. And we can, again, use like train them efficiently by sampling random layers. And now, instead of them being closed-form Gaussians, of course, they are closed-form categoricals. So you can also jump to kind of scramble to any layer here. This is closed form. You can use base rule. This is also closed form. So everything works out very nicely, as in the Gaussian case. So at a high level, the main difference is really that we replace the Gaussian with a categorical. And there's, of course, some kind of details as to how you parameterize this and so on to make it work well. But I won't go into detail here. And here is an example on yeah, the kind of the generation process of a sentence. So up here we sample some uniform categorical noise, and those are kind of, I mean, each character is one dimension, so you get some completely random characters here, and then you start running that through the trained kind of denoising or decoder model, and it kind of, you can see structure will gradually appear until you have something that looks almost like a sentence. It's not completely perfect, but it is, most of the words kind of make sense. So yeah. So that's diffusion models on text. Everything the same as diffusion models for images. The difference is you use categorical distributions here instead of Gaussians, and then you can train them on text and yeah, learn very flexible distributions over categorical data. So that's it really. So maybe one final thing I can add is what connects these models, and you can say superficially there's nothing really that connects them, other than that they're generative models and so on. But actually, in the continuous time case, so both for flows and diffusion models, you can go to the continuous time case. There's actually some beautiful connections between them. And so flows in continuous time become ODEs, ordinal differential equations. And diffusion models can be viewed as stochastic differential equations. And there are papers on doing both of these. And actually, for the stochastic differential equations, you can often convert them into an equivalent ODE. So you can basically train a diffusion model, and then after training, you can convert that into an ODE that gives you the same distribution, and then you essentially have a flow at test time. But this is a newer work that I didn't really cover here. But yeah, so they have some connection, but not really in what I covered here. So yeah, that's it. Thanks for listening.